Start recording. Hello, this is the recording for the homework solutions for problem 3. So I'm just going to go through and record all of the things that I owe you. Notice that I put headings behind me. Every problem in this homework set can be done the same way. So you first understand what's going on in a cartoon, diagrams, write down Newton's laws, and then solve for the things you need. The first problem asks you to imagine a person in an elevator. Here's an elevator car. The acceleration of this car may vary, but the person is just standing right here. Now, the only forces that act on them, remember, are gravity and things that physically touch them. And the only thing touching them is the elevator floor. So gravity goes down, and the normal force from the elevator floor goes up. Acceleration is not a force. Whether this is plus or minus 4 meters per second, or it's 0, whether it's that, minus 4 meters per second squared, or 0, these are the only forces you've got. Newton's laws of motion, again, well, sum of the forces equals ma. We've only got one direction and one object, so I have one equation. I'm just going to have that the normal force minus mg equals ma. Here we'll choose the conventional coordinate system where up is positive. Now, in this problem, I'm asking you to figure out how big each of these forces are. And I tell you that the person has a mass of 60 kilograms. So, this weight force, right, mg, is always going to be 60 kilograms times 10 meters per second squared, which is 600 newtons. But the normal force, I don't know. The normal force is however big it needs to be to keep her accelerating with the elevator floor. So I can solve for the normal force. So let's just solve for F sub n. F sub n equals, well, this goes to the other side. So ma plus mg. And for the different values of a, we can figure out what we get. So let's make this a bit simpler. The normal force is going to be the mass of the person times a plus g. So we have a couple of different values for the acceleration. If a is plus 4 meters per second squared going upward, then the normal force is going to be, let's see, this is 60 kilograms times 10 plus 4 meters per second squared, which is, let's see, 60 times 14, that's going to be 840 newtons. Likewise, if the acceleration is 0, then the normal force is just mg, which is 600 newtons. And finally, if the elevator is accelerating down, then the normal force is it would be 60 kilograms times 6, which is 360 newtons. Just put in parentheses here, this value is 60 kilograms times 10 meters per second squared minus 4 meters per second squared. So what we see is that the normal force is largest when we're accelerating upwards, and intermediate value when we're not accelerating, and smallest when we're accelerating downwards. That's problem 1. Problem 2 asks you to think about what that means. So I can't go right up and down an elevator right now because I'm plugged into the power outlet. But when you do this, if you go do that, you will notice that when you're accelerating upward, you feel heavier. When you're accelerating downward, you feel lighter. And when you're not accelerating, you feel normal. So what you'll learn is the thing that determines how heavy you feel is not your weight. So notice, let's put over here, is your weight is always 600 newtons, but the normal force is 360 newtons if you're accelerating up, 600 newtons when you're not accelerating, and 840 newtons, 360 newtons accelerating down. That's totally wrong. 840 newtons accelerating up. So the conclusion is that this is your apparent weight. How heavy you feel is the normal force of the floor on you. So we get that your apparent weight is the normal force from the floor. So that's problem 2. I'm going to just check something very briefly on my computer. Make sure that everything is working as it should be. Yes, it is. Okay, let's move on to problem 3. Problem 3 is the locomotive problem. So in this problem, I'm going to briefly rearrange my headers because a train is longer than it is wide. So I'm going to put my cartoon here. I'm going to put my diagrams here. And I know that the algebra will take a little bit more board space here. So I'm just going to move this. Algebra. It's the same process now. So what do we have? We've got our locomotive, labeled as L. We know it's a locomotive because it's puffing out smoke. It's pulling a train with 2 cars. We'll label these cars 1 and 2. A different color here, don't I? This one we'll label as 1. And then the one behind it we'll label as 2. And the locomotive, since it has an engine, it's very heavy. It has a mass that's 3 times as big as the others. We'll put that in later. Hi, Nathan. No, I am not the goat. So the force diagrams for these 3, again, just think about what forces act on them. The thing you have to be careful with here is traction acts on the locomotive going forwards, right? Its wheels are being turned by the engine, and those wheels are pushing the locomotive forwards, whereas friction pulls the others backwards. Because the locomotive is being powered, but the cars are not. Now, I'm going to omit a diagram or omit forces going vertically. I know they're not going to do anything interesting, so they're just going to be canceled out by the normal force. The only thing the vertical direction will tell me is that the tracks support all of the train cars, right? There's a train track here. But I don't care. All right, here's the locomotive. It is being pulled forward by the traction from its wheels. Remember, they're being turned by the engine. And it's being pulled backwards, use yellow for this, by the force on the locomotive from car 1. So that notation means force on locomotive from car 1. All right, what's going on with car 2? Well, it's connected to the locomotive. Locomotive pulls it forwards. Force on car 1 from locomotive. Car 2 pulls it backwards. F1, 2. And friction pulls it backwards. What shall we use for friction? We'll use white for friction. No, we'll use pink. Where'd my pink chalk go? F, frick. Car 2, same business. Car 1 pulls it forward. Force on 2 from 1. And friction pulls it to the left. All right. So those are the force diagrams. Notice I've kind of given you a bit of a spoiler. I have color-coded the forces that are Newton's third law pairs. The force on car 1 from car 2 is the same as the force on car 2 and from car 1. I also need to choose a coordinate system. I'll choose the one that you probably all picked, where to the right is positive. So now I'm just going to read off of these my equations. So for the locomotive, locomotive gets an orange header. I have the force of traction minus the force from car 1 equals the mass of the locomotive times the acceleration. Notice I'm using the same acceleration value for all the cars. They're all coupled together. They all accelerate in the same way down the tracks. So I can make life simpler that way. Excuse me. Allergic to talk dust. For car 1, let's see, I've got 1 force going forwards and 2 going backwards. Oh. L1. So here I have F1L, force on 1 from locomotive, minus these 2 that go in the other direction, minus F frick, minus F12 equals M1A. And then for car 2, same deal. I have F21 minus F frick equals m2a. All right, so now it's time to start putting in things we know and solving for things we don't. I've already put in the fact that the acceleration is the same for everybody. I also know that the locomotive has 3 times the mass of the others. So I could, at this point, just come by and do this with my eraser. So that's 3ma. Oop, this is problem 3. This is just ma. This is also just ma. All right, that's nice. So I'm here trying to figure out the force of friction. That's what I want. Or excuse me, no. The force of traction. That's what I want. But I have other unknowns in this problem too. I don't know the forces that the train cars exert on each other. But I know that they are equal. Remember, Newton's third law says if one thing pulls on another, then that thing pulls back. So I've really only got 3 unknowns: the traction force, the force of the locomotive on the first car, and the force of the first car on the second car. So here's a tip. This is the thing I want. The easiest approach is to start on the other side of the equations. So what I'm going to do is I'm going to go to equation 2. I'm going to solve for F21, and I'm going to substitute it here. Then I'm going to solve for F1L and substitute it here, and then I'm finally going to find the traction force. So let's do this. So I'm going to take equation number 2. I'm going to move F fric to the other side, so I get F21 equals ma plus F fric. All right, got one of them. And let's check them all and make sure they make sense. This tells me that car 1 must pull car 2 with enough force to overcome the friction in car 2's wheels, plus enough to make it accelerate at the desired amount. Okay, that's nice. So now I'm going to take this and I'm going to substitute it into equation 1 for car 1. So let's see, this tells me F1L minus F fric, and now I substitute that stuff in. So minus ma plus F fric. So all of this got substituted here equals ma. Now, I came here to learn F1L, the force that the locomotive must pull car 1 with. So I throw everybody to the other side. And that gives me that F1L equals, I can just combine terms. So this gives me 2ma plus 2F fric. Well, that makes sense. If a locomotive is trying to pull a train made out of 2 cars, then the locomotive must pull those cars with enough force to accelerate them, plus enough force to overcome their friction. Now finally, I'm going to substitute that back into the equation for the locomotive. All right, so I'm going to take this and put it in here. So for the locomotive, I have F track. Where are we? Oops. Minus all of this stuff, 2ma plus 2F fric. This all got substituted here, equals 3ma. Finally, solving for f track, I get f track equals, combining terms, 5ma plus 2f fric. This makes sense as well. There's friction in two cars' wheels that I have to overcome, and the train is, the locomotive has to apply an additional amount of force to give the needed acceleration to 5m worth of train cars. I want to highlight here the way we solved the system of equations. We knew this was our goal, so we started far away from it, solve for one variable, plug in, solve for a variable, plug in, solve for a variable, plug in, solve for the thing we want. Don't do shenanigans involving adding equations together. Yes, I know you did that in the 8th grade. It's correct, but it's almost always the hard way to do it. All right. Let's move on to problem 4. Now, I'm going to be a little bit snarky in doing problems 4 and 5. And you'll see why. So, if you're prepared for sarcasm, good. Okay. There's not going to be much algebra here. We're mostly interested in cartoons and diagrams. So I'm going to redo my headers. Notice it's always the same headers. All right. So problem 4 asks you to imagine a 1 kilogram book on a horizontal frictionless table. So we have a table here. The table doesn't move. We have a 1 kilogram object, and something mysterious pushes down on it at an angle 30 degrees from the vertical. So there's some push coming in here. At 30 degrees. This force here is 9.8 newtons. Now, for the force diagram, what do I have? Well, remember we are in space where there is no gravity. I have a normal force acting up on the object, which we'll draw in orange. Right? Because if I'm pressing down on it, the table will press up. And this force, we'll label it F push, goes at a 30-degree angle from the vertical. Now, we're going to need to decompose that vector into components. So this one, let's see, that's the opposite. So that's Fp sine theta. And this one, vertical one, is Fp cosine theta. Notice you cannot memorize x is cosine and y is sine. You always have to think about which one is adjacent and opposite. Okay. Now, Newton's laws in x and y. In the x direction, well, I've only got one thing in the x direction, right? Fp sine theta equals max. Got two things in the y direction. I have a normal force minus Fp cosine theta equals MAY. Now, I know a few things here. Specifically, I know that the object doesn't move through the table. So that's 0. The problem asks you to identify these terms, right? So what did I say? I wrote, underneath your equation, write the meaning of each term in words. Use language such as the component of blank parallel to blank. So, actually I should give myself more room here. So we'll do that. So this is component of push parallel to the surface. And then for the other one, for y, let's see, we have Fp cosine theta, that's got a minus sign, plus Fn equals MAY. Some color coding. And this term is the component of the push that's perpendicular to the surface. And obviously this is the normal force. Now, where were we? We know that this doesn't accelerate in the y direction because we know it doesn't move through the surface. That makes life easy because that allows us to find the normal force pretty readily. Let's do the algebra. All right, this is easy. A sub x equals Fp sine theta divided by m. That's 9.8 meters per second squared. Times the sine of 30 degrees, which we know is 1/2, divided by, 9.8 newtons. Out of myself. Divided by 1 kilogram. And that's just 4.9 meters per second squared. Here, the normal force is just going to be the component of the push perpendicular to the surface. That makes sense, right? If I'm pushing down on it, whatever the component is with which I'm pushing it into the table, this one right here, has to be counterbalanced by the normal force for it to not move through the table. So I don't know off the top of my head what the cosine of 30 times 9.8 is, so I'm going to have to ask the Google machine. Give me just 1 minute. So 9.8 times the cosine of 30 degrees is 8.5, 8.49, whatever. So what's going on? Well, the component of the pushing force that is perpendicular to the surface gets opposed by the normal force, right? The table pushes it up. but the component of the normal force that is parallel to the surface produces an acceleration because there's nothing to oppose it. Now, I told you that I would do problems 4 and 5 all in one go. How am I going to do that? So you've probably figured out the trick by now. This is just a thing sliding down an inclined plane but tilted, right? 9.8 newtons happens to be the weight of this object here on Earth. So I did problem 4, now I'm going to do problem 5. Ready? So the push force rather than Fp is now gravity. Now it's not a mysterious push in space, it's Earth's gravity. But its magnitude is still 9.8 newtons. Right, all I'm doing is I'm changing the push forces to mg. Now, we'll draw these arrows slightly differently, just for grins. Of course, the diagram is the precision thing. So that's mg. This is mg, and you're probably thinking, wait a minute, gravity doesn't go at a funny angle, gravity goes down. And you told me to do this problem on a slope. Well, one of the advantages of online teaching is that I can just do the problem on a slope. So, welcome to our fancy sloped world now. Hi. Yes, I know there's a monitor clipping through things. Now gravity goes straight down. This is straight down, right? We're on a slope, and our coordinate axis, right? We often talk about a tilted coordinate axis. Now I'm drawing this so it looks straight on my board, but notice this is the same tilted coordinate axis we've been using in class. Right? I have a thing sliding down an angle, an incline, and I've decomposed the force of gravity into a component parallel to the surface, which winds up being mg sine theta, and a component perpendicular to the surface, which is mg cosine theta. This is opposed by the normal force, right? Because the surface is flat like this. Yes, it's tilted, right? I went up to the board and I drew a flat line, but the point of these paired problems is to get you to see that the tilted coordinate axis is very natural. I had you do the inclined, something sliding down an inclined plane first in disguise. So I'm now going to go back and untilt my camera and we'll do the rest of the homework set. So here we go. I'm going to zoom in, reframe. There we go. All right, on to problem 6. Problem 6 reminds you that kinematics exists. This one is simple enough that we don't really need their diagrams. So this says a 1,500 kilogram car is driving at 20 meters per second. The driver wants to stop over 30 meters. What force must the brakes apply to do this? Well, remember in recitation, you derived this formula that relates ending velocity, starting velocity, and acceleration. This is sometimes called the third kinematics equation. So in this case, we know all of the quantities. We know the final velocity is, looking at my screen, forgetting what number I gave you. No, front driver's stopping, so 0. We were starting at 20 meters per second squared. The distance here is 30 meters. Now, the acceleration we don't know. So the strategy here is going to be to find the acceleration using kinematics and then stick that into Newton's second law. So the plan here use kinematics up there to find the acceleration. Then use F equals ma to find F. Once you have this plan, it's incredibly straightforward. So I get minus v naught squared equals 2a delta x. I know delta x, right? The problem tells me that it's 20 meters. So let's see, I'm supposed to find a and then use F equals ma to find F. So I get an acceleration of minus v naught squared over delta x. Now I'm going to go ahead and put in the numbers here because this can tell us, this can give us some insight in how big that acceleration is. So 20 meters per second, or excuse me, meters per second squared. Speeds are in meters per second, dummy. So 20 meters per second squared, all of that squared, divided by 30 meters. This gives me 400 meters squared per second squared, divided by 30 meters. So let's see, that's 40 over 3, which is 16.7. Meters squared per second squared divided by meters is meters per second squared. I appear to have goofed in, whoops, I forgot the 2. I was going to say that, so this is why it's always good to check these things. This is wrong. I know it's wrong because this acceleration is faster than g. And you know the force of static friction is the normal force times mu. Mu can't be greater than 1, so I can't actually decelerate this fast. All the numbers in the problems for this class, remember, are realistic. I forgot this factor of 2. So apologies to all of you who have been howling at me watching this on YouTube, saying, you forgot the 2. Yes, there's a 2 there, which means rather than dividing by 30, I should be dividing by 60 meters, which means my value for the acceleration ought to be half that, which is 8.3 meters per second squared. That's about the acceleration you can get doing a complete slam on the brakes, panic stop in a car with very good tires and anti-lock brakes. So now we want to find the force. So F equals ma the mass was 1,500 newtons times 8.3 meters per second squared. So let's see, 1,500 times 8.3, so 1,500 times 8 is the same as 3,000 times 4, which is 12,000. And then 0.3 times 1,500 is another 450. So this would be 12,450 newtons. That's a really big force. Whoops, no. What am I doing? 1,500 kilograms is the mass of the car. And if you think about it, this car weighs about 15,000 newtons, so its brakes are applying a force to it almost as big as its weight. So that's problem 6. That's fairly straightforward. It's mostly here to remind you of the kinematics that you learned. You could also do this problem if you didn't remember this relation that you derived in homework 2. You could also do this by writing down the time and position equation, or the position as a function of time and the velocity as a function of time equations separately and substituting. On to the last one, problem 7. So problem 7 was a game in vector addition. I tell you that there is a sled sitting on the snow. We're going to use this conventional coordinate system. We're also going to use the conventional compass directions. Let's see. 3 people are pulling on it with ropes. The first rope points 45 degrees north of east. So we'll color code these. And I've told you it is 45 degrees north of east. So east, swing north. And this force is 200 newtons. Another one points south, and someone pulls on it with a force of 300 newtons. There's no trig to do here. And then the final rope points 30 degrees north of west, and the force on it is 200 newtons. And we can label these that's F3, F1, and F2. The question says, you want to pull on it with some other force to stop it from moving. Which direction and how hard should you pull? So there's a fourth force, F4, that we don't know about. We're trying to find it. What we know is that F1 plus F2 plus F3 plus the one we want to know, F4, all of that adds to 0. So what I'm going to do is I'm going to decompose all of these vectors into components and use that to solve for the components of F4. So what that means, right, F4 is equal to the negative of all of those added together. So minus F1 plus F2 plus F3. So really, now all I need to do is add them up and take the negative. So now we do our trig. So F1x is going to be 200 newtons cosine 45 degrees, which is 141 newtons. F1y is going to be 200 newtons times sine 45 degrees, which is also 141 newtons. Now, F2 is going in the minus y, so F2 is that ordered pair. We could write here this like this, so 141 newtons, comma 141 newtons, writing this in ordered pair notation. F3, let's see, F3x is going to be minus 200 cosine 30 degrees. I don't remember that off the top of my head, so please forgive me a Google. That's 173. This one, F3y, is 100 newtons, because the sine of 30 degrees is 1/2. Now, there are a bunch of ways you can write this and organize it. Let's just write right down here, say, well, we'll collect it over here. So, this is negative. F1 is the ordered pair, 141 newtons, comma 141 newtons. F2 is nothing in the x direction and minus 300 newtons in the y direction. F3 is, whoops, that one's supposed to be yellow. So it's negative in both x and y, right? It's pointing to the left. Whoops, it's positive in y. I was right the first time. I'm tired. So that's positive, but no, that one was negative. Dumb. The y component is positive. Oh, I know what I messed up, right? Let's just do this again. X component is minus 173 newtons. The y component is plus 100 newtons. They say never do math live on Twitch. So F4 then is negative the sum of those. So I'm just going to add them up. So let's see, I have 141 minus 173. This would give me minus 32, but I take the negative, so it's plus 32 newtons. And I've got 141, 241 minus 300 gives me minus 59. But that would become plus 59 newtons. Now, the question doesn't ask you for x and y components. The question asks you for magnitude and direction. So let's see, I've got a vector here. F4. Its x component is 32. Its y component is 59. I can use the Pythagorean theorem to find that hypotenuse. So let's do that. Square root of 32 squared plus 59 squared. Type it into Google correctly this time. Gives me 67 newtons. That's from the Pythagorean theorem. And to find the angle of this angle, this is the inverse tangent of 59 over 32, which I can type into a calculator. Let's see. Arc 59 over 32 in degrees, which gives me 62 degrees. So this other rope you have to pull with would be like that, F4. Boop. And it's nowhere near as big as the others. It's only 67 newtons and the others are 200 and so on. So this question was just reminding you how vectors worked, in case you had forgotten. So these are the solutions to homework set 3. If you have any questions about any of this, please talk to me, talk to one of the folks in the physics clinic. I'm going to stop the recording here, and I will see you all later.